In this section, we're going to explore another test for showing whether a series is convergent or divergent that involves comparing that series to one that we already know something about. And this is particularly useful for ones that resemble p-series, because we know exactly when p-series are convergent or divergent. So if I can easily make a comparison between a given series and a p-series, oftentimes that's going to be a very helpful way of determining whether that series is convergent or divergent. Let's take, for instance, these two series here, the series 1 over 2 to the n, and then something kind of similar, but not quite, 1 over 2 to the n plus 1. Now we know that 1 over 2 to the n is convergent because this is a geometric series. Remember, this is a geometric series. With r equal to 1/2, right? Because the sum would be 1/2, 1/4, 1/8, and so on, right? So yeah, we're multiplying each consecutive term by 1/2 to get the next term of the series. And so it's a geometric series with a common ratio of 1/2. And since here the absolute value of r is less than 1, that means it's convergent. And in fact, we can get the actual sum of this series if we want to. But let's take for a moment a series that looks very similar but is slightly different. Notice that this one is no longer geometric. So I can't use the same argument that we did over here to say that it's convergent. But what I can do is I can compare the terms of this series with the terms of the geometric series that we know about. So how do those two terms compare? So how does 1 over 2 to the n plus 1 compare with 1 over 2 to the n? And what I notice is that because 1 over 2 to the n has a smaller denominator than 1 over 2 to the n plus 1, the overall value when I divide will be bigger. So the one that has the bigger value in the denominator will be smaller overall. So what we see is that the terms of the series 1 over 2 to the n plus 1 are smaller than the terms of the series 1 over 2 to the n. Therefore, we can say that the sum of 1 over 2 to the n is going to be bigger than the sum of 1 over 2 to the n plus 1. So what does this tell us? Well, since we know this actually converges to a value, this one must also converge since it's smaller than something that we know converges. So it's smaller than, in this case, the sum of the series, right? Well, what does that mean? If it's smaller than some finite value, then it must also be a finite value. So it implies that it also is convergent. So that's one way we can use the comparison test, is to directly compare the terms of two series. In this case, I'm comparing it with a series that we already know something about because we know everything about geometric series. And therefore, something that resembles that series here, in this case, because we know it has smaller terms than the series that we know about, it must also converge because the sum must be smaller than something that we know adds to a finite value. Let's try it with this example here. Now this is a little different. Here we're comparing 1 over the square root of n with 1 over the square root of n minus 1. Notice that here, 1 over the square root of n is a p-series, right? It's like 1 over n to the 1/2 power. So it's a p-series, in this case with p equal to 1/2. And since, yeah, that's a value that's less than or equal to 1, means that it's divergent. Okay. So again, we know everything about the p-series 1 over the square root of n. And the question is, well, what about this one that looks very similar to it, 1 over the square root of n minus 1? It's not quite the same, but because it resembles this other p-series, let's see how these two terms would compare. So again, let's compare the terms of 1 over the square root of n with the terms of 1 over the square root of n minus 1. Now notice that here the bigger denominator is in 1 over the square root of n. This one is being subtracted 1, so this denominator is smaller, therefore the overall quotient here is bigger. Right? And over here, the one with the bigger denominator has the smaller overall quotient. Now looking at it this way, it looks like here, if I were to compare their sums, the sum of 1 over the square root of n compared with the sum of 1 over the square root of n minus 1, well, now this guy has to be bigger than something that we know is divergent. So if this one's divergent, remember divergent means that this is an infinite sum. In other words, it sums to something that goes to infinity. So here we can think of the sum goes to infinity. Versus 1 over the square root of n minus 1, which is a bigger sum, so must also go to infinity. Because it's bigger than something that sums to infinity. So therefore also divergent. So you see the argument was mostly directly comparing the terms of one series to another, where we know something about one of those series, and if the other series has bigger terms, then, well, here we just have to show that, okay, if the terms are bigger than something that we know is divergent, then it must also diverge. Or like in the previous example, we saw that the terms were smaller than the terms of a series we knew were convergent, and so that series must also converge. Okay, so the direction that this inequality symbol is going is actually very important here. So that's something to keep in mind, is that if the inequality symbol were going the other direction in this case, we wouldn't be able to make the same argument. So let's establish this more officially here. So what we're calling the comparison test says that suppose we have two series, each with positive terms, where one of the series is convergent. We know, for instance, that the Bn series is convergent. And if the Bn series, think of that as the one that we already know something about. It's like a p-series or a geometric series, one that's really easy to tell whether it's convergent or divergent. And the An series is something that resembles it in some way, or one that we can say, for instance, has terms that are less than or equal to the terms of Bn. In that case, then, if the Bn series is convergent, then the smaller series must also be convergent. So if the Bn series is convergent and the terms An are less than or equal to the terms Bn for all n, then the sum of An must also be convergent. Okay? On the other hand, suppose that we know that Bn is divergent and the terms of An are bigger than the terms of Bn. Then An must also be divergent. So notice, for showing divergence, we have to pay attention to the direction that this inequality symbol is pointing in. So this inequality symbol is very important, and is the key part to the argument that you're making in the comparison test. So we'll try and make our argument carefully when we're using this version of the comparison test. Let's try an example. Suppose we want to determine whether the series 5 over 2n squared plus 4n plus v plus 3 converges or diverges. And so one easy way to determine what we want to compare it with is to just take the dominant terms of this series. And by dominant, I mean the ones with the highest degree terms. So we're going to take the dominant terms, and that'll be our Bn series. Okay, so Bn here would be, we'll just say 5 over 2n squared. And now I want to compare the Bn here with the An. So in this case, 5 over 2n squared plus 4n plus 3 compared with just 5 over 2n squared. Now the one that has the bigger denominator has the one with more terms added there below. So that quotient is going to be smaller. And we know that the series 5 over 2n squared, notice I can take the 5 over 2 out of the series. That doesn't make a difference here, whether it converges or not. So really, the series is a multiple of the p series 1 over n squared. And so this is a convergent p series. Right, you can see that here p is 2, which is bigger than 1, so that means it's convergent. And since the terms of the other series are smaller than a convergent series, it must also be convergent. So the series we're looking at originally here must also converge because the one we're comparing it with has bigger terms and is convergent as well. And here I'll say it also converges by a comparison test. Let's do another example where we can try and compare the series with something that we know something about already. Here we've got the series ln of k over k. Now, it's not entirely obvious because here ln of k is not necessarily a polynomial, but we can always say this about ln of k. ln of k is always going to be greater than 1. And or at least eventually, right? And therefore ln of k over k will be greater than 1 over k. So that tells us now we should make our comparison with the series 1 over k. So what do we know about this series 1 over k? Well, notice this is the harmonic series. And remember, we know that the harmonic series is divergent. Right? Remember, it's a harmonic series, or you could also use a p series. This is also a p series with p equals 1. But we've shown in a couple ways that here now the harmonic series we know is divergent. So p series with p equals to 1, which is definitely greater than or equal to 1, or sorry, less than or equal to 1. Okay, so we have a couple ways to explain why 1 over k is divergent now. And since ln of k over k has bigger terms than 1 over k, Therefore, it must also be divergent. And in this case, by comparison test, since we were comparing it with some known series. Okay, so just a couple of notes that I want to mention here. Although the condition an is less than or equal to bn, or an is greater than or equal to bn in the comparison test is given for all n, we need verify only that it holds for some n greater than or equal to uppercase N, where uppercase N is some fixed integer because the convergence of a series is not affected by a finite number of terms. Okay, so what they're saying there is that this inequality argument that you're making doesn't need to hold for all n, only for n beyond some certain cutoff. So another note is that the terms of the series being tested must be smaller than those of a convergent series or larger than those of a divergent series. So again, the direction of that inequality is really an important part of the argument that you're making. And if the terms are larger than the terms of a convergent series or smaller than those of a divergent series, then the comparison test doesn't apply. But we have another version of the comparison test that will allow us to address those situations. And so if that's the case, the series, in other words, the series that we want to compare it with, doesn't satisfy that inequality argument that we're trying to make with the comparison test, then we can use the limit comparison test instead, and that will give us the same result in a way that doesn't involve that inequality argument.